In this video, I'm going to be talking about TCP congestion control. Now, this is a huge topic, a complex topic, and it's by far the most in development portion of TCP because it really makes TCP what it is today. And the reason you can watch this video on YouTube is because of advanced congestion control. Okay, what is it? Well, let's see if I can define it. Congestion control is TCP's method of adapting to network conditions and dealing with packet loss in a graceful way. Okay. So basically, it's adapting to network conditions and dealing with packet loss. I guess I did define it. So, but there's about 50 different versions, and almost every OS manufacturer seems to have its own way of doing these things. Okay, let's start with the first thing, adapting to network conditions. What does that mean? It means that TCP will manage its flow rate. It will sense the capacity of that network path, which is always changing. Every network is constantly in flux. That's all. Well, okay, not every network. Your LAN at home, if you have a wired network, yeah, that's pretty stable. But we're talking internet here, and it's going to be constantly in a changing state. And so TCP has to use complex mathematics in order to deal with the packet loss when it happens, but also make sure the send rate is as fast as it can go. So different network conditions like mobile networks have very high delay, whereas your wired, say your cable connection is going to have a lot less delay. And so TCP is going to adapt to those kinds of connections. It's going to be going through different routers of different bandwidth. So say your router, you have 10 megabit upstream, but you have a gigabit LAN. TCP has to be able to work with that scenario, work with your router, and not just overwhelm your router and just packets just drop constantly. Okay, so how does it manage flow rate? Well, flow rate is it uses a concept called a window. A window is a range of sequence numbers, which sequence numbers equal bytes. So one sequence number equals 1 byte of data. So it's a range of sequence numbers that get burst out in sequence. And that range of sequence numbers has to be fully acknowledged before another range of sequence numbers, another window, can be sent. So say if there's a range of 100 sequence numbers in one window, which is going to equal multiple packets. Well, not 100 sequence numbers. Okay, that's less than a packet. But say 50,000. Okay, that's more than one packet. It's going to be the range of sequence numbers is going to push out the sending side, and then all of that has to be acknowledged on the way until another window comes back. And the windows are constantly in flux. So if you look at Wireshark and you do a capture and you look at the window graph, you're going to see it's up and down and it's all over the place because they're constantly changing. And that's TCP's adjustments. TCP's constantly adjusting based on the window's influenced by the receive buffer of the receiving device because it can only receive so much. So it's constantly reporting back what it can receive. So if you look at a TCP packet, you're going to see in the layer 4 header, you're going to see a window. You're going to see a number in there. And that's the receiving device reporting back to the sender, hey, don't go past this. Okay, and there's that. But also, TCP is going to be, most of the time, in most congestion control algorithms, it's going to actually purposely induce loss. So it's going to spike it first in order to sense the capacity of that network. It's a concept called slow start. I'll be telling you more about that later. But once it hits that threshold, so once the send rate, those windows get huge, it's going to, there's inevitably going to be loss. And now that's TCP's measurement. It knows the capacity of that network, at least at that time. So from there on out, things become a little more stable, but depending on the congestion control algorithm that's in use, depending on the operating system, it's going to still continuously, purposely induce loss because it's trying to max out. It's trying to feel out the capacity. It's trying to beat the other connections. Each TCP connection is going to try and beat the other concurrent connections. It's trying to push its way through the UDP and all this other stuff. TCP is a bit of a bully, depending on which algorithm you're using. But yeah, it's a bit of a bully. It tries to use as much capacity of the network as possible. Now, I said the word capacity. Now, I like to think of the network path as almost like a storage medium, because it kind of is. It's very temporary, but think about it. From host to host, those bytes get sent out, and there is a period of time in which those bytes consume the cabling, the routers, the switches, everything. And it's a very temporary storage medium. Well, the fastest possible flow rate is consuming all of that capacity. So almost like a flash drive, filling up that flash drive and then keeping it full. So it's filling up that capacity and keeping it full. So finding a window, so TCP's at its absolute fastest when it has a window that consumes the entire capacity of that storage, which is the network, which is the cabling and everything else. And then all of that gets pumped into the receiving device. All of those acknowledgments come back, and then another huge window comes back and fills out that whole capacity. Now, the network capacity elongates. It gets bigger when delay is added. So it gets longer, some physically, geographically longer, because geographical distance adds delay, but also router buffers, switches, all the stuff in between in a network adds delay. And the more delay, that means it could fit a bigger window. And the more bandwidth also means it fits a bigger window. So this is why you might, if you're reading about congestion control, you might read about the bandwidth delay product. Bandwidth times delay equals the maximum window size. So, and that makes perfect sense. So if you have, I don't know, a 10 gigabit link to the dark side of the moon, right? It's going to have massive delay, and so it's going to have massive delay and massive bandwidth. Your window's going to be huge. But if you have a 64K modem just to the computer next to you, things are going to look a little bit different, or no, never mind. That was a stupid example. How about my gigabit LAN, which I have tiny delay, but I have lots of bandwidth. So that calculation of those windows are going to adjust to those network conditions. So in a gigabit LAN, most likely you're going to overwhelm the receiving device before you're going to overwhelm your cable. So when things do get overwhelmed, what happens? There's packet loss. Well, from the sending device's perspective, because the sending device is the device that has the congestion control capacity. It's the device that has to take care of the send rate. Back in the past, the sending device had no way of managing its own send rate. However, now the sending device has to know when there's packet loss. And really, there's two kinds of packet loss. There's timer-based packet loss, whereas that's typically a pretty bad problem. That's when a range of sequence number leaves, and there is a timer that gets kicked off. It's called RTO, retransmission timeout. A timer gets kicked off if an acknowledgement for that if those sequence numbers don't come back in that time. That's a timer-based retransmission, and a retransmit has to happen. And then it slowly backs off from there. So the time in between retransmissions backs off until a reset is sent. And so at that point, the connection is completely closed. But typically that is a bad scenario, because either the packet itself is completely lost, which that's fine, but also it could be that the acknowledgement is lost. That could also happen. Well, and remember, it also could be a checksum error. It could be a checksum problem, because in TCP, unlike UDP, a checksum is mandatory and it covers both the header and the data. In UDP, it's optional and it only covers the header. But so a checksum error could be packet loss. But RTO, that's usually a severing of the path or a router that's completely grossly overwhelmed. It's a pretty serious problem. Or there is a device is just down, and somehow a reset isn't getting sent. So you're trying to send, you're like, say, sending a reset to a machine that doesn't exist, right? You're going to see that RTO occur. That's one type of packet loss. That's severe, but there's minor packet loss. Minor packet loss is when bidirectional communication is still fully functional. And so if, say, 10 packets in a window, say you have a window of 1,000 packets and then 10 of them get lost, there's a range that got lost. Well, the receiving side is going to acknowledge the all the way up until that lost point, and then from there it's going to send duplicates of that previous acknowledgement, and these are called duplicate ACKs. If you've done any packet captures, you've probably seen duplicate ACKs. And these duplicate ACKs, they're not delayed, so it's not every other packet, it's every one. So as the rest of that window comes in, every single packet is going to generate a duplicate ACK. And so it's absolutely going to be screaming at the sending device, we have a packet loss. We have massive packet loss. When the sending device receives 3 duplicate ACKs, which it's going to very quickly, it's going to then resend whatever is missing. And there's a lot of technology that goes into that process. In fact, that process of dealing with minor packet loss really is the bulk of congestion control, and a lot of the debate of what's best and the best method of dealing with that packet loss, and then adjusting that window size accordingly after the packet loss occurs. So the questions are, do you cut the send rate completely in half and then step it up slowly? Or do you cut the send rate into 3/4 and then step it up really fast to get your send rate back up? I mean, how do you do that without completely compromising the network and causing congestion collapse? Which I'm going to go into that in a later video, but that's the debate, is how to deal with loss while potentially some of them actually try to avoid loss. Those are called congestion avoidance algorithms, and those are new and experimental. And you may be watching this video using a congestion avoidance algorithm because it's on YouTube, and a certain percentage of YouTube videos, Google is testing a very advanced version of congestion control called BBR, and BBR actively tries to avoid packet loss while using complex mathematics and measuring round trip time, that delay, by using delay calculations to try and accurately send packets, adjust that window size perfectly in order to avoid packet loss. That's you know, that is really cool stuff, but also very, very complex. Okay, so I think I covered the very basics. So in the next series of videos, the next bunch of videos, it's going to be a lot. So I guess you can call it a series. I'm going to be talking about the history of congestion control. And because there is some cool stuff in the history of why it came to be. And there is a lot of really interesting papers that were written back in the 80s that really laid the groundwork for the modern protocols that we're using right now today. And I'm going to be going into the different technologies. So there's slow start, there's RTO, there's fast retransmit, fast recovery, there's TCP, Reno, Tahoe, Vegas, there's BIC and Cubic is what I'm using right here. And there's so much to it. It's a huge topic. So I'll get working on that. All right. I hope you learned something. Thanks for watching.